Helping someone with a $20 bus pass usually hits a wall of friction. If they don't have a bank account or a crypto wallet, traditional systems force them through days of paperwork or technical onboarding just to receive a small act of support. We solve this by using a program-derived address, or PDA. A funder deposits USDC into this account, which is controlled entirely by code rather than a private key. The program generates a unique 7-character alphanumeric string that serves as the specific requirement for release. The smart contract manages 2 specific state transitions. If a recipient provides the matching data string, the program validates the code and moves the status from funded to released. If the preset timeout is reached first, the funds are programmatically routed back to the funder's address. By settling this in 400 milliseconds for less than a cent, we bypass the heavy bureaucracy of traditional aid. Because recipients don't wait days for banks to clear, the technology effectively recedes, focusing on the immediate need. This creates a security challenge. Traditional crypto relies on heavy public onboarding to verify transactions, but we want a light, plain text flow for people under stress. On a public ledger where every piece of data is transparent, a simple code would normally be visible to anyone watching the network. We resolve this by ensuring the plain text secret never actually touches the blockchain. We split the data. The readable code stays on the funder's device, while the Solana ledger only holds a cryptographic representation of that secret. Before the transaction is finalized, the app combines the code with a random string of data called a salt. This is processed through a hash function to create a unique hash. Only this scrambled version is stored on-chain, making it impossible for an observer to work backward and find the original code. This architecture secures the funds against public theft, while allowing the recipient to claim them using nothing more than the original text message or a piece of paper. Building this logic in Rust, the primary language for Solana, requires a shift in mindset. Compared to Python, Rust is famously strict, stalling often during development as it forces you to account for details that other languages might ignore. We can see that contrast here. Python handles variables dynamically and lets errors bubble up through exceptions. In Rust, variables are immutable by default, and we must use the question mark operator to explicitly handle every potential failure path before the code will even compile. This strictness is vital because of our design constraints. To prevent human typos, we use short 7-character codes. While this helps a person in a high-stress situation, it also makes the code vulnerable to automated bots that can guess thousands of combinations in seconds. Consider the engineering requirement. We need to block a bot from rapid-fire guessing without permanently locking out a human who simply made a mistake. We have to build this protection directly into the on-chain state. Our solution is an on-chain progressive cooldown mechanism. This logic enforces a mandatory wait time that increases after every failed attempt. We implement this by adding 3 specific fields to our escrow account struct. We track the current number of attempts, the maximum allowed tries, and a timestamp recording exactly when the last attempt occurred. Every time a claim fails, the program calculates a new wait period that grows exponentially. The question mark operator ensures the program correctly pulls the current cluster time. If the cooldown hasn't passed, the transaction is rejected before it can even check the code. This creates a mathematical barrier that stops automated guessing in its tracks, while keeping the system accessible for a human user who might need a few minutes to double-check their note. There is one final hurdle. Even with a secure code, every Solana transaction requires a network fee. A recipient with no wallet or digital currency has no way to pay this fee to claim their support. We resolve this with a gasless relayer. This backend service intercepts the recipient's claim, co-signs the transaction as the fee payer, and broadcasts it to the network. The recipient gets their funds at 0 cost. This completes the full-stack architecture. The front end generates the readable code and computes the hash locally. The middle-tier relayer sponsors transaction fees, shielding users from gas costs. Finally, the on-chain layer is the immutable record, verifying hashes and enforcing attempt limits. By layering these 3 systems, we've built a path where the technical requirements of the blockchain disappear. The result is a system that handles the movement of value as efficiently as the internet moves information.